Okay, so I'm going to start by looking at the first thing I posted the other day. And forgive the background noise, I'm actually in my car right now, and it's raining pretty hard, so if you hear the rain, I apologize. But I'm not going to reshoot this. So, hopefully you can hear okay. Um, the units that that we're going to use are the SI base units. And the SI base units for every unit are the SI system is the international system of measure. There's also the English system of measure, or the imperial system, and that uses feet and miles and pounds. And there's the metric system, which is a little different. The difference between the metric system and uh, the SI system is that the SI system uses kilograms as the base unit for mass, where the metric system uses grams, which is the base unit. But that has to do with how forces are defined based on standardized masses of 1 kilogram. So we use the kilogram as our standardized mass, but really the key variables here are length, mass, and time, the second. All right, length, time, and mass. Those are the three standardized units that are defined quantities, which are different than the derived quantities. All the derived quantities are derived from either length squared is area, length cubed is volume. If you take a length and divide by dimension of time, so we're talking about dimensions, we're talking about the physical quantities of length, mass, and time that are used to derive area, which is a measure of a surface, volume, which is a measure of a size of an object, in 3 dimensions of length. So you get like a length times width times height. Those are 3 length dimensions. And then speed, that's a length divided by time. That's a rate of change of position, how quickly an object's moving. It could be in miles per hour or meters per second. Now, acceleration, if you take a velocity like 0 to 60 in 4 seconds versus 0 to 60 in 12 seconds, one of those is fast, right? The other's slow, but that change in velocity over change in time, the rate of change of velocity, how quickly something's speeding up or how quickly something's slowing down, is measured in meters per second, which is meters per second squared, which is where it's a rate of change of velocity, versus speed, meters per second, that's a rate of change of position. This is a rate of change of meters per second, or velocity per unit time. So that's indicated here. And then when we start incorporating mass, we can get momentum, mass times velocity, or force is mass times acceleration. Now we can get into more abstract quantities if we multiply a force over a distance, like the energy that you expend by lifting a particular amount of weight or jogging a particular amount of distance, because you have to exert a force on the pavement to jog. You're going to have to expend energy. And that's essentially what your muscles do in your body, is they exert a force over a distance, and if they exert a bigger force over that same distance, they expend more energy. And, if you were exercising and doing resistance training, you try to rapidly do that so that you could get some cardio, and that would be your power. That's the rate of energy production, is power, or the rate of energy consumption. Now you can talk about density, that's mass divided by volume. The reason that's important is because air density has to do with drag forces and other things, and so does pressure. So all of our physical quantities that we have here are all some fundamental they're either derived units or they're defined units. The only defined units are length, mass, and time. There are other defined SI base units like charge, the unit of a coulomb, or temperature, degrees Kelvin would be other SI base units, but these are the base units of mechanics, which deals with motion and forces of large objects. So the interesting one is time. Right here it measures as 9 6,192,631,700 energy level transmissions of an electron in a cesium-133 isotope. This is the mechanism for an atomic clock, which is a very, very, very high precision. The precision is so high that it's going to be, after 138 million years, that clock's going to be off by less than a second. And that level of precision is why we have the capacity to do things like GPS, because they can very precisely measure time and synchronize the way different satellites that are orbiting in different orbital trajectories are pinging at the same instance in time. And where you on the surface of the Earth determines when that instance in time, the difference in time from when you hear those different radio pings from those different satellites, is able to triangulate your position and calculate with the sphere of the Earth where the intersection of those four spheres, with those 4 points in time, would be. Is essentially how that works geometrically. It's called triangulation, but it uses a computer calculation that's pretty complicated but simple in principle, because the only measurement that really matters is time, and everything else is geometry there. With the GPS system and how it works, and uses radio waves to calculate your exact position. And because you have such precision with your time measurement, you can have accuracy with your precision on Earth within 10 feet, so that you can get those turn-by-turn directions, which is important for GPS. It's also important for guided missiles and smart bombs, so to speak, because they can eliminate collateral damage by being highly precise with their targeting. Another thing we have here is the note sheet. This gives you 3 separate derived equations: equation 1, equation 2, and equation 3. Now, if you're an algebra person, you really like the algebra, you can actually take those 3 equations and algebraically derive the equation card formulas. But the reason we have those equation card formulas the way we do here is they're organized in a relatively commonly used form, like VF equals VI plus AT. This is the linear form of if acceleration's constant and velocity is at the start and the end of an interval of motion, as something's speeding up along a straight line track, like a railroad track, then, or a straight one directional linear motion, then your equation is going to be this. This acceleration is a constant value, but the velocity is changing, but it's changing linearly over time, because the acceleration is the meters per second squared times seconds is meters per second equals meters per second plus meters per second squared times meters per second is meters per second. The units have to be the same across this equation. You can't add unlike units. You can only add like units. But when you multiply or divide in an equation, those units, you can do the same math on them and they'll always check out. So d, distance, or displacement, actually what it's called is displacement, because that has a direction, just like velocity and acceleration have a direction associated with them. But displacement is units of meters. Alright, so you have meters divided by seconds squared times time in seconds squared gives you units of meters. So this term has units of meters. This term is velocity times time. Meters per second times seconds gives you meters. So this is meters equals meters plus meters. You can't add unlike units. Like, what does it make sense? It doesn't make sense to say meters is a, what do I get when I add 15 minutes and 100 meters? You can't add unlike units, but you can multiply those unlike units to make something with new dimensions. Just as VF squared equals VI squared plus 2AD. This is meters per second squared times meters gives you meters squared over second squared, which is the units of velocity squared, which is what we have for those units as well. So the units will always check out. An interval of motion will always be assumed to have the same uniform acceleration over that interval, because we're dealing with uniformly accelerated motion. Otherwise, we'd have to use calculus if we had non-constant motion. So the other definitions here are just kind of things that you could look at on this interval and get an idea of what we're talking about. When we say delta anything, delta is the triangle in front. That means change in. All right, so change in position is delta x. That's displacement. Position final minus position initial is equal to change in position. Velocity final minus velocity initial is change in velocity. The mathematical similarity between change in position over change in time and change in velocity and change in time is what makes the velocity position acceleration relationship deal with rates of change. So we'll look at that a little bit more in detail next. So this note sheet has your ticker tape lab information. You can think of this as like a little lab notebook that's kind of condensed onto one page here. Trying to be concise with the space and say a lot in a little bit of space, so it doesn't take that long to go through. So if you have to look at it a couple times, just check out this video, and hopefully this will explain what you need to put on the write-up. The write-up is basically just verbalizing the whole problem-solving situation from start to finish. So the key to think about the entire time is the objective. That's the experimentally determine the free fall acceleration, which is the acceleration due to gravity, using a ticker timer. So when an object's in free fall, it's assumed to have the only force acting on it is the force of gravity, and hypothetically, eventually it would get at faster and faster rates. This doesn't happen because of air resistance, because air resistance is a velocity-dependent force, and it happens, it doesn't affect objects that are of high density at low speeds. If you have a heavy mass, like 500 grams or heavier, it's going to be able to pull a light little paper strip through this machine, which has the ticking arm ticking 60 times per second. And what's not drawn on here is normally you'd have like a carbon paper wheel that would print little dots on there, and you try not to have it hit too hard on the tape, because if it did, then you wouldn't have true free fall and you'd have error. And that error is kind of intentionally worked into the data that you have, to where you should see a value that's lower than the theoretical value of the acceleration due to gravity, which is 9.8 meters per second squared. So just as a point of reference, because perspective is really important, 10 meters per second is about as fast as a human being can run. That represents a top speed of 100-meter dash running in like 10 seconds, which is really, really fast, like Olympic sprinter level. After about 1 second of free fall, an object is falling faster than a human being can run. After 2 seconds of free fall, it will have sped up by that same amount every second that goes by. So meters per second squared means that every second that passes while an object's in free fall, it speeds up by 9.806 meters per second. So that's a rate of increase of velocity, ignoring air resistance, ignoring all other forces. So if you have a situation like what we're doing in the lab here, this may not be true free fall, but we're assuming it is for the sake of determining the experimental acceleration. So the theoretical value is 9.8. That's what it theoretically should be. But when we conduct this experiment and we get this real motion diagram of dots on this ticker tape, the end of which may be a result, because maybe this is how high the desk was that you dropped from, whatever D11 is, this was after it hit the ground, so the ticks bunched together. So we're kind of using like some circumstantial evidence here, but we're measuring the distances over time, and with that we can calculate a bunch of separate points that are the total distance and the total tick number for that point. Well, if each of these distances here, starting from the origin, the zero position, and then we take this to be the positive direction, then we look at the displacement and time data can be calculated to have average velocities over each interval. And if we assume uniform acceleration, which this is one of the equations that requires that assumption, you're basically saying you can average the endpoints as long as it's speeding up at a constant, steady rate. Well, all of our linear motion is going to be uniformly accelerated if we're calculating it by hand. But if that's the case, then the average velocity is twice the final velocity, because VF over 2 is equal to the average velocity. So you can simply double those average velocities for every point as you calculate them and graph them. And then the trend line function on Excel, the purpose of that is to take this data set and produce what's called a line of best fit. And all that line of best fit is a straight line that minimizes the error, minimizes the distance that these points are off. So if you see dots that are kind of hanging down at the end here, that you can probably just ignore them from the data set, because you can assume that was not during free fall. And during the period of free fall, you should see a steady increase in the velocity over time. And that steady increase, the slope of that data set, is the value of the trend line. That's like y equals ax plus b, or y equals mx plus b, vf equals vi plus at, or a being the slope, t would be the x value, this is the x-axis, the y value would be the final velocity or instantaneous velocity at each point, because the final velocity at the end of any interval here is the velocity that it has at the instant that tick number gets made. The total number of ticks and the total displacement to that point can be used to calculate what the instantaneous velocity is as it hits that point there. And that's actually the data that we're using here. There is an assumption that kind of goes with that it's uniformly accelerated, but it turns out that assumption's pretty good when you see that the data set is pretty linear. So getting the function, either Excel or Sheets, sometimes there's different nuances to that, to spit out the trend line with the equation displayed. So on Sheets, you have to select the marker. On Excel, there's a right click a data point, so you put your cursor right over a data point, you'd right click it with the mouse, and then it would have add trend line, and you want to scroll down and choose to display the equation on the chart. Sometimes you look at an r squared value. The closer to 1 an r squared value, the better the linear fit is. We should get pretty much 1 as an r squared value for a data set, at least for the data set that you have. So if you have questions about doing that data analysis or what to put on the write-up, then definitely feel free to contact me through the announcements or through the class discussion. And hopefully this helps clarify what the first task is.